post the recording onto the e-spectrum for those who are not able to join us today. Right, so this week is week 11, right? So week 11 until week 14. Actually, for today, supposedly we should have an invited industrial a webinar by the industrial partner, but the speaker sent me a message on Monday saying that he couldn't make it today because of he has another important meeting with his collaborator, so that the meeting, the webinar has been postponed to next week. So next week we are going to meet online via, not via this Microsoft Teams platform, but via Google Meet, because the speaker he doesn't has an account for Microsoft Teams. So we will listen to his talk, because for this course, for Dr. Khor's part, we learn about all those atomic spectroscopic techniques, right? So we want to know whether is it important for us to learn all the knowledge of those atomic spectroscopic techniques, and is it really useful when it comes to industry, right? If let's say after your final year either project or internship, right? So would it be useful if you learn this course, the topics as discussed in this course? Is it really useful for you to use in industry one day in the future, right? So that's why we want our faculty, or actually should be encourages us to have this kind of at least one slot for every single course offered by chemistry department to have this session with the industry partner, right? So so this week we are going to discuss, because we have two tutorials, we don't have mid-semester test, right? So these two tutorials, Dr. Khor's part, we have 10%, 5 for tutorial 1, another 5% for tutorial 2. So make sure students, you submit all your tutorial answers. Then if your answers are correct, then I will give you full marks, 10 marks for my part, and then another 10 marks for continuous assessment from Professor Sharifa, and then 30 marks from your practical class, your lab reports or whatever activities that your lecturer asks you to perform. So for the final exam, we do summative assessment. Prof Sharifa will give you 25%, and my part is the final exam, which is scheduled on the 30th of June, end of next month, the last day of next month. We will sit for 1 hour of final exam, and I will give you 30 minutes for you to submit your answer script. I will talk to you this in detail. So this week we have our tutorial 1 answers discussion, and then next week we have an invitation talk, a webinar by the industrial partner, and then week 13, because for your summative assessment, Prof. Sharifa requested to have a meeting with you guys on the last week, which is week 14. So on week 14, both slot, Tuesday slot and also the Thursday slot, will be taken by Prof. Sharifa. So I will meet you on week 13 for 2 slots, both slots, Tuesday morning and also Thursday morning, right? To discuss all the answers and also to answer any queries that you have during our pre-recorded lectures. Right, so now today I would like to share with you my screen first. I will give you a brief introduction on what we have discussed in our pre-recorded lectures. So let me share my screen. Okay, so can you see my screen, students?
Yes, doctor.
Yes, doctor. Yeah. Okay, so let me give you a brief, quick briefing before we continue with our tutorial 1 answers discussion, right? So as you can see from this screen, this is the summary on what we have learned for atomic spectroscopic techniques. Okay, so can students tell me what are the 3 important components in this study, in these topics, these important topics, atomic spectroscopy? What are the 3 important components that you can see from this slide? Give me some feedback. Because this is a tutorial discussion, right? So that students, if you have any question, you can raise the questions and I will try my best to answer all your questions, right? So I want a two-way interactions. Otherwise, like in the last 9 weeks, we always have pre-recorded lectures, right? So I do not know whether students you follow or not my lectures. So this is the chance for our synchronous lectures, we can have a two-way discussion, right? So please participate actively in our discussion, right? So for atomic spectroscopy, it depends on which technique we are talking about, but basically there are 3 important components for these techniques. So can students tell me what are the 3 important components? Any one of you? There's no right or wrong.
Light source.
Good students. Light source, we have light source. Yes, and also
detector.
yes, and also detector. There's the most important 3 important components, right? So how to differentiate between atomic emission, AES, AAS, and AFS? For AAS and AFS, these 2 techniques, it has 3 important components: the light source, the atomizer, and the detector. And for these 2 techniques, AAS and AFS, these 2 techniques are meant for single elemental analysis. Means that for every single experiment, right, it only can detect one type of analyte at the same time, single element, right? Because we know that atomic spectroscopy is meant for elemental analysis, right? Don't ask me what is element. Element, you have the periodic tables, right? So you have 118 elements in total, right? So, but not all the elements in the periodic table that could be detected by all these 3 techniques, right? So maybe for AS is suitable for certain group of elements. For AES, for AFS, not all the elements in our periodic table could be detected by using these atomic spectroscopic techniques, right? So for AES, what's so special about AES is, as compared to AS and AFS, is this AES is meant for multi-elemental analysis. So within a single test run, it can detect more than one element, right? For AS and AFS, no. It only can detect one element at one point of time, right? One element. Why? What limits that this AAS and AFS can detect only one element at one point of time? It is because of the light source. You see, very clearly, for AS and AFS, we have light source. For AS, we do not have a light source. We have a source that could allow us to perform atomization as well as excitation. 2 important processes happening in this source. We don't call it as atomizer. Why we cannot call for AES this source as atomizer? Because if it is atomizer like here in AAS and AFS, we call it as atomizer because the function is only meant for atomization, right? However, for the excitation, for AAS and AFS, the excitation is due to the light source, the light source here that caused the excitation. In contrast, in AES, we don't call it as atomizer because it is not only meant for atomization, but it also meant for excitation. So that's why we cannot call this as atomizer. We have to call it as a source, energy source that allow us to perform atomization as well as excitation, right? So how to differentiate between this AAS and AFS? AS, the signal that we want to determine is the absorption, excitation, how much light being absorbed, right? In contrast, for AFS, what we measure, this one also involves excitation, right? If there is an excitation, there is an absorption. However, the signal that what we want to detect is the emission signal. And this emission signal is not any emission signal, but it is a fluorescent signal that we want to measure. So that is how we differentiate between this AAS and AFS. And another important thing that you have to pay attention is the position of the light source between the AAS and the AFS. If you look at AAS, it is placed in parallel with the atomizer and the detector. And what's the problem if, let's say, we have the light source being placed in parallel with the atomizer and the detector? It will give us some background issues. So that's why for AS, most of the time, we have to perform background corrections. In contrast, for AFS, if you look at the position of the light source, it will never be placed in parallel with the atomizer and most importantly, the detector. So there must be an angle mounted, not in parallel. The best position is at 90 degrees, right? But sometimes 45 degrees or more than 0 degrees. As long as it is not in parallel, then it would be good. So what's special about this AFS, right? After the atomized atom being excited, they will relax to the ground state and emit fluorescence radiation. So when we detect the fluorescence radiation, right, by using the detector, we do not need to perform any background correction because the position of the light source is not in parallel, most importantly, with the detector. Right. So for this, as I mentioned, in AS and in AFS, the excitation is caused due to the light source, right? So for this, in contrast, for AES, the excitation is caused by the energy source, not atomizer, energy source, right? So the temperature of the energy source is very important, right? We must have a well control on the temperature of this energy source. If there's any slight change in the temperature of this energy source, it will affect the population of the excited atoms, the excited population, excited atoms, because this will definitely affect the signal that we detect, because the signal is the emission of electromagnetic radiation. Once it gets relaxed to the ground state, it will emit electromagnetic radiation, which is the signal that we want to detect using the detector, right? So for these two techniques, AAS and AFS, temperature of the atomizer, not much impact towards the excitation of the analyte, the target analyte, because the excitation is due to the light source. But for this, again, I would like to emphasize for atomic emission spectroscopic AES, the temperature of the energy source is very important. We must have well control. But in reality, in practical, it is hard to control unless we use ICP. If we use flame, arc and spark, it is so difficult for us to control the temperature, and hence it will affect the population of the excited atoms, right? And it will affect this detection, the signal detection, electromagnetic radiation by the detector. And hence, in order to solve this problem, we need an internal standard. Okay, so this is the summary that what we have, and a comparison and all the comparisons between all these basic atomic spectroscopic techniques, AES, AAS, AFS. So in industry, people use a lot of this AAS, either flame AAS, graphite furnace AAS, right? So for this specialized technique in AAS, perhaps only in research universities like right? We will go for this co-vapor or hydrate generation, right? But in the industry, seldom you heard that they have this instrument at their workplace, right? For AES, this is a common, but not flame AES, is ICP AES or ICP OES. A lot of company, they do have this instrument, especially for those who work on elemental analysis for environmental sample analysis like water analysis. They have this ICP AES. They cannot afford to have ICP-MS is because ICP-MS is very expensive. And also, since ICP-AES also perform multi-elemental analysis, so a lot of industry. So you learn this topic is useful. Who knows that one day in the future you're going to work in a company that has this instrument that you can be the specialist expert using that instrument in the future when you work in industry some after your graduation. For this AFS, this is most of the time we know the theory, but even a lot of university, we do not have this instrument, right? Because it is quite a new technique as compared to this AES and AAS, and also not easy to have this actually as long as we have ICP-MS, because most of the university, they do have ICP-MS, right? Why we still want to go for this? But there is some of the university, they do have this AFS in their university, right? So now I'm done with this brief introduction. So now I would like to move on to have a discussion with you on the answers for our tutorial 1. Okay, so for this tutorial 1, the first question, we have in total 6 questions. I will try my best to finish as many questions as possible today. If cannot, we will continue on week 13, right? So in the determination of mercury using atomic absorption spectroscopy, mercury must be present in the light path as what? Which is the answer? So before this, we have to, because this multiple choice questions, for your information, the final exam question already been set for my part, and we have vetted the question, and some of the questions are they are multiple choice questions, right? So multiple choice question, it seems easier, right? As compared to structure questions, means that something like this, a question, and I ask you to give a short discussion, short explanation. This is a structure question. Sometimes the short essay question is even easier as compared to multiple choice question, because multiple choice question sometimes it really needs your critical thinking before you can pick up the correct answer, right? So for this first question, talking about detection of mercury using which technique? AAS. So this question is about AAS, because all these questions, they are mixture of AAS and AES, right? So I would like students, you are able, when you look at the question, you are able to know that this question actually belongs to which topic, either it is AS, AES, or AFS. So this question is very clear. We know that this question is about AS. So your mind, your thinking, you should focus on AS, what you have learned in that particular topic, AAS. Okay, so now we want to determine mercury. So how to determine mercury using an AAS technique? AAS technique, right? So the mercury must be present in the light path as what? The unexcited neutral atom. Can any one of you give me the answer? Any one of you? Lee Boon Hong, can you please give me the answer?
Yes, doctor. My answer is A.
A. Why you pick A?
Um, because the mercury must be present in light path should be an excited neutral atom, and the AS is for the measure the atomized neutral state. So my answer should be A. Yeah.
A. So why not B? Why not C? Why not D? Why not E? Huh?
Because C and D should be eliminated because AS is measure the atomized vapor, atomized elemental vapor. So C and D should be not correct. And E, because they mention organometallic complex, so I also eliminate. I also delete this answer. So I
Why
just consider
you
A
think
and
this
B
is not the correct answer for E?
because this is the organometallic complex. So for the lecture notes, I didn't see any organometallic complex in this AS topic. So I delete the answer for E. So I only consider A and B. So A and B, because the B is the excited neutral atom, right? So it shouldn't be excited neutral atom. So I consider A. I only consider the answer for A.
Good answer. So on top of what has been mentioned by Mr. Lee Boon Hong, I would like to add on, because this is a complex, right? So what we want to detect in AS is the atomized atom. So if it is a complex, then we cannot detect, right? So automatically E is not the correct answer. So C and D also not correct, because this is droplets, micro-sized droplets of the liquid, not even after the atomization, right? So this is a crystal, solid, so totally out, right? So now we want to look at either whether it is A or B. A is unexcited neutral atom, because in A, as we know that the excitation is due to the light source, right? So it has to be in unexcited. And neutral, this is the keyword neutral. Why neutral is important? Because we want it is at zero charge, right? Not the ionic stage, right? When we do the atomization, it's just to convert it from molecules, from complex, right, into an atom, a neutral atom, not the ionized. Ionized, either it is a cation or anion. Most of the time it's cation, right? ICP-MS, right? So it is a neutral, right? So this is excited. Not this is the difference between A and B is one is unexcited, one is excited. Excited is wrong, because we want to determine mercury using AAS in the light path, right? The light path, the light source is the component that cause the excitation, right? So it has to be at the atomic stage, neutral atomic stage, vapor state, vapor, not even the solid, vapor in the gaseous form at the unexcited state, not the excited state. So the answer is A. Thank you very much, Lee. So now we move on to question number 2. Zinc has its first resonance line at this wavelength, nanometer. With the same acetylene air flame, the detection limit is much lower or better with the atomic emission flame spectrometry, because of what? Before we pick up the correct answer, we have to understand the question itself first. So this question is about what? This question is about a comparison between what? Comparison between what? So can any one of the students let me know what is the comparison? I would like to invite Fariha Sakina to join our discussion. Can you please tell me
Yes.
this question is about comparison between which technique? If you look at question number 2, because this is the way I have discussion with you to let you understand critically the topic. It's not like I tell you the answer. I can post the answer on the spectrum. I will do that later on after we finish our discussion, right? But I want you to understand the concept of every single technique that we learn, right? And do comparison between each technique. That is important. That is the purpose why we want to learn, okay? So please help me to answer this question. Fariha?
My answer is
I
D.
don't want your answer first. I
Oh,
want you to answer my first question. This question is about comparison of between which technique?
I think between AES and AAS.
AAS
And
compared
AES.
with the AAS, compared with this AES,
AES.
flame, right? So it says that the detection limit, when we talk about detection limit, is about what? It's about the sensitivity of detection, isn't it? How low we can detect, right? Let's say for this elemental analysis, usually we want to detect at low concentration, trace concentration, ultra low concentration, right? So if let's say we use this AAS, we able to detect the target analyte at low concentration, much lower concentration, right? It gives us signal as compared with the AES, right? So what element we want to detect here in this study is zinc.
Zinc.
Zinc is the target analyte, right? So we know that every single element, they have their characteristic wavelength, right? So for zinc, the characteristic wavelength, one of the characteristic wavelength is at 213.9. This 213.9 is for AAS and also for AES. So what is the difference? Why these both technique AAS and AES have the same characteristic wavelength? Should they have the same characteristic wavelength? For zinc, should it be the same characteristic wavelength?
Yes.
Yes, it should be, because this characteristic wavelength represent this is zinc element, identity of zinc. If other characteristic wavelength represent other element, right? Just how to differentiate between this? This for AAS is a black line, characteristic wavelength, black line. If you still remember that I have shown you, okay, so if it is AES, you will get this color line. You see color line. If it is AAS, you will get a dark black line. This same spectrum, right? Same characteristic wavelength for the same element. Just that to differentiate between AES and AAS is, in AES is a colored line. In AAS, absorption, because you already absorb the light. So at that particular characteristic wavelength, you will get a dark color, black color line, spectra for your AES, AAS spectra. AES spectra, AES spectrum, spectrum. Spectrum is for single, right? So now we move on. It says that you will get a much sensitive detection in AAS as compared to AES. Okay, so why? Which is the correct answer? So thank you, Fariha, for answering the first part of the question. Now I would like to invite. Wow, I have in total 34 students, but now I only have 23 students joining this meeting. All right. So I would like to invite Risma to pick an answer for question number 2. Which is the correct answer for question number 2? Rishma, are you with us? Are you online?
Yes, doctor.
Yes, good morning. Can you pick the answer for us? A, B, C, D, or E? Which answer?
A.
You choose A. A is the zinc halocated lamp is very intense. Why you pick A? A is it? Did I receive your message correctly? Just now you mentioned A, is it?
Yes, I mentioned A, Doctor.
So why you pick A? Why
I
you
thought
pick A?
like if the
Mm,
hello cathode lamp is very intense, then the sensitivity will be better.
the sensitivity. So would this apply to AAS? Because we are comparing AAS, right? First, we must understand the question, what the question asks. So this question is about the comparison between AAS and AES, right? So you pick A. The answer is you say you think that the light source, the halocathode lamp, the zinc halocathode lamp is very intense. So is this question if we only talk about if we pick A, right? So it is relevant to AES. So why not you you pick A, why not you pick other answers? Why not you pick why you think B is wrong? Absorption uses a chopper and a lock-in amplifier. Absorption uses a chopper and a lock-in amplifier. So do you think B? You don't think B is the correct answer, isn't it? Otherwise you won't pick A, right?
Yes, but I'm not sure about the other answers, Doctor.
Okay, so let us go through together, So that's why we need to have discussion, and joining this tutorial answer discussion is extremely important. You're not only know the answer, right? But you understood every single answer, why you not picking it or why you pick it, right? And also you will have a chance to listen to the explanation that you might miss during the pre-recorded lectures. Maybe when you listen, you don't understand. So now you listen it again, then you can ask question on the spot if you have any questions, right? So it's important. Encourage your friends to join our meeting, if they don't join today, right? See, absorption is based on measuring a small difference in large signal. Why do you think C is not correct? Maybe I could ask someone else to help you. I would like to ask this Muhammad Sabri Mirza. Can you help our friend? Just now I asked whom?
Hi.
Just now.
Yeah, I'm here.
Uh,
I choose C.
This is the answer, cannot show you. You choose C.
Yeah.
C. Absorption is based on measuring a small difference in large signal. Why you choose C?
Because it says that atomic emission is better than AAS, right? Here, the question. Is it?
No, the question is, it said, with the same ethylene air flame. This acetylene air flame is the atomizer, right? So it says that the detection is much lower than with the atomic emission spectroscopy because of what?
Oh, yeah, this question, I don't really understand. So the
Question is, okay, now we want to detect zinc. Okay, so we want to compare AS with AES, right? We want to compare AS and AES. See which technique can give us the sensitive detection. And this is just to tell us the characteristic wavelength for zinc, because this is atomic spectroscopic techniques, right? So it says that if, let's say, as compared with this AES, we will get much lower detection limit. If let's say we can get lower detection limit, means we have a better sensitivity. Better sensitivity means what? Let's say at this ppm ppb lah. Let's say we say about ppb level, ppb. But for this flame, it's difficult to go to ppb. Okay, let's say we say ppm level, for flame ppm, right? So for graphite furnace, we can go to ppb, but for flame, most of the time is at ppm level. Okay, let's say for flame AAS, this is flame, flame AAS versus flame AES, right? So the detection limit is much lower for flame AAS. Then means we compare with AES, right? Detection limit is much lower. That means that at this ppm level, let's say we can detect zinc at 1 ppm or 0.1 ppm. 0.1 will be the sub ppm. Okay, let's say we say 1 ppm. We say 1 ppm. We can have a better signal if we use flame AAS, that we can get a much lower detection limit, means more sensitive. At 1 ppm level of zinc, we use AS, we can detect it, right? But if let's say we use flame AES, atomic emission flame spectroscopy, AES, flame AES, we are not able to get a good signal, right? Maybe when we detect with flame AES, non-detectable. So that is the detection limit is much lower. Or here, better. Flame AAS, better than flame AES. Why? What is the explanation behind? Why, when I want to detect zinc, I use these two techniques, flame AAS and flame AES. If I use flame AAS, I can detect at low concentration. Detection limit is much lower. At 1 ppm, I'm able to detect zinc, use flame AAS, right? But I am not able to detect good, cannot get a good signal if I use flame AES. Why? Because of what? Is it A, B, C, D? Of course, D is not, right? Because one of A, B, C, D would be the answer. So just now, the first student, she answered that she picked A, right? Why she picked A? She said that the zinc halocathode lamp is very intense. Zinc cathode lamp. So, is it intense? Intense means very high energy, right? Most of the time, because this is a comparison between AS and AES, right? We learned that from AS, AES, and AFS, right? So for AS, now we're not focusing on AS only. We are comparing between AS and AES. And another thing is the answer for A is not so correct, huh? For the first student that answered this question, this is not the correct answer that to this question number 2. Why I say this is not? Because is even though that it is very intense, that it will not give us to make a comparison between the AS, and it will not answer the comparison between AS and AES. And another thing is, we know that what would be affect the signal of detection if let's say we use higher energy of light source. It's only in AFS, atomic fluorescence spectroscopy, right? But not for this AAS, right? So for AS light source, we learn, right? So we learn 2 light sources in AAS. Either it is a halocathode lamp or electrodeless discharge lamp, right? So it doesn't mean that you have higher energy of light source, you will make the detection sensitivity higher. It's not for the case in AAS, but only in AFS, atomic fluorescence, right? So the difference between AS, for AS, the halocathode lamp and also the electrodeless discharge lamp is because this electrodeless discharge lamp is meant for excitation of those highly volatile elements. So that's why we have 2 options. It's not about the intensity or intense, very intense or high energy of the light source. It wouldn't have much difference for AAS. But for AFS technique, yes, it will, right? So, and also we are not picking up the answer for A is because this question is about the comparison between AAS and AES. So this is not quite a suitable answer because one of the answer, it might be the main reason, because main reason to explain why if we use flame AS, we will get a better sensitivity of detection. Detection limit is much lower, means that you can detect at low concentration. but not for AES. If you use AES technique to detect the same target analyte, zinc element. Okay, so answer B is totally out because this is not relevant at all to this question. Let's look at C. Why C is correct or not correct? The answer is not the correct answer, right? Now we want to explain why it is not the correct answer. Absorption is based on measuring a small difference in large signal. What does it mean? Based on measuring small difference in large signal? It is not answering at all to this question to make comparison between AAS and AES. Okay, so measuring a small difference. Okay, we know that if there is a small change in concentration, then it gives us a big change in the signal. The signal, either it is for AS is absorption signal, AES is emission signal, right? So that is related to sensitivity. So this answer number C, it is not answering this question number 2 at all. It's talking about absorption is based on measuring a small difference in large signal. No, we know that absorption is based on how much of the neutral unexcited atom being excited to the excited state. That is about the absorption, the definition of absorption, right? So in your final exam question, they are a basic question based on the concept of your understanding. What is excitation? What is relaxation? You must know all these things because this is the basic, the principle of this atomic spectroscopy. How does this atom being excited from the ground state to the excited state? Because of what? When it absorbs energy from the electromagnetic radiation. It has energy, then it can excite. Otherwise, how to excite, right? So this definition is wrong and also is not answering question number 2. How about D? This acetylene air flame, this is the atomizer, right? So both technique, flame AS and flame AES, using the same atomizer, which is the acetylene air flame. And we know that this acetylene air flame, right? What would it affect, right? This atomizer, would it affect towards this AS and AES? Would this detection, right? We know that detection for AS is the absorption. The excitation for AS is caused by the light source, right? So for this AES, the excitation is caused by what? By the energy, right? By the energy source. By the energy source, which is the acetylene air flame. We know that this is a low temperature flame, right? So if let's say we have a low temperature flame, we cannot, this energy source in AES, just now I mentioned during my brief summary, right? I mentioned that this source is meant for 2 important functions. One is for atomization, another one is for excitation, right? So if it is low energy source, right? So it can perform atomization, but it might not perform well, right? Or even it might not perform well, full atomization, right? And also to cause all the neutral unexcited atom to get excited. If let's say in AES, the target analyte is not fully atomized and not excited to the excited state, when it relaxes, it won't emit the signal, the radiation emission, right? Full signal to represent the concentration of the target analyte, right? So that's why you cannot be able to detect, right, sensitively using this AES because of the low temperature of this flame. Acetylene air flame is not energetic enough to excite large number of zinc atom. If cannot excite, means that your signal, you cannot get a good signal. At low concentration, you get low signal. Means that this technique is not as elegant as flame AS. Because for flame AS, whether you have this acetylene flame is only for the function of atomization. It's not for the function of excitation. Excitation is due to the light source. So that's why at low concentration, if possible, we always go for atomic absorption spectroscopy instead of atomic emission spectroscopy. Unless we use ICP AES or ICP OES, right? Which is high energy enough to excite all the elements that we want to detect. Okay, so if let's say for low temperature flame, right? For AES is the atomizer, for AES is the source, right? So this one, it might only useful for group 1. Group 1, the alkali metal elements in your periodic table. But for zinc, the transition metal, it needs high energy to excite the zinc. We know that every single atom, it has the orbital, electron orbital SPD, right? Right? For zinc, it needs high energy to get excited from ground state to the excited state. So if let's say you only use flame, it is hard for us to excite zinc with low temperature flame. Okay, so this is the explanation for question number 2. Right, so now we move on to question number 3. In a hot flame, okay, so far student, are you okay with the explanation? Do you understand? If you have question, you please ask. Please ask. This is, we only meet another 4 weeks, including today. 4 session, 4 hours. So if you have question, please ask. Now we move on. Yep. I hear some voice.
What is the can you repeat the answer? Is it B?
Yes, the answer is D. D.
Yeah, right.
Because for this acetylene, our target analyte is what analyte? It's zinc. It's a transition metal, right? So we need high energy. If for AS, we need high energy, temperature of the energy source to excite this zinc, right? So if let's say we use this acetylene air flame, low energy, we are not able to excite. If we are not able to excite zinc from ground state to the excited state, means that you have very low concentration of the excited population, right? So when it relaxes to the ground state, you get very low signal or even no signal or even no signal because of none of the neutral atom, unexcited neutral atom at the ground state cannot be excited to the excited state. If we use this energy source, the acetylene air flame for zinc detection. If let's say, if we want to use acetylene as this flame, it is only suitable for detection of group 1. The group 1, you know our periodic table, right? Our periodic table give you some periodic table, right? So group 1, low energy, right? Low energy flame, then you can excite this group of elements. For transition metal like zinc, difficult, right? Difficult. You're not able to excite. So that's why you cannot detect. You have to use, or we have to use AAS. We have to use AAS because AF no problem. We have the light source to excite, to excite the zinc atom, neutral atom, unexcited atom from the ground state to the excited state. So the answer is D. Correct answer is D. So now,
excuse me, doctor. Just want to clarify the answer in D, the acetylene air flame is in terms of AES or AAS?
both.
Both.
Both. This acetylene air, in AS, it is the atomizer. Because in AS, we have atomizer, we have flame, right? Flame atomizer. We have graphite furnace, right?
Okay.
In AS, Okay, so this is the AS topic. So the atomization technique, we have what? Flame. Air acetylene flame. Okay, low temperature flame, right? So we have what else? Graphite furnace, electrothermal, right? So this is specialized technique, glow discharge, and also hydrate generation and cold vapor. These are all the atomization technique. So this question, we use acetylene flame. This is the keywords, acetylene air flame, right? For our detection. So for AS, this is the atomizer. For AES, this is the energy source. Means that acetylene air is used for AES, is used for atomization and excitation. For AS, it's only meant for atomization.
Okay. Okay, thank you.
Okay, so don't confuse because this, why we want to do tutorial? Because when we learn each topic AS, we learn, right? We cannot link between AS and AES, cannot link between AS and AFS. So tutorial is very important. Tutorial discussion is extremely important because it gives us the overall picture, how to link between AS, AES, and AFS. So you must attend this tutorial answer discussion session. So now we move on to question number 3. We only have 7 minutes, but I want to precious every minute that we have. In a hot flame, if we cannot finish, no worries. We continue on week 13, because next week is our industrial talk. In a hot flame, the emission intensity of the sodium line at this wavelength, this is the characteristic wavelength, it is greater in a sample solution that contains KCl then when this compound is absent. Suggest an explanation. Okay, so this question is about what? This question is about what? It's about which technique. We are talking about which technique. Is it AS, AES, or AFS? Which technique?
AES.
AAS?
AES.
AES. Good student. It is about AES. So we use AES to detect what?
The emission of the
We want to
the
use
radiations.
AES to detect which element?
Sodium.
We want to detect sodium. Sodium is which group of element?
Group 1.
Group 1 element. So this AES technique, of course, it has emission spectrum, right? Characteristic this wavelength at 589 and 589.0.6. So this is the these are the characteristic wavelength for sodium. So use AES technique. So this question is about, if let's say when I want to detect sodium, right, I add something in my sample solution, sodium solution. I add what? I add potassium chloride. Then I will get a greater signal, emission signal, because this is AES, right? So I get greater emission signal. So I have a better sensitivity if I add potassium chloride in my sample solution as compared if I do not add. This compound is absent, means that I do not add this potassium chloride in my sodium sample solution, right? Suggest an explanation. Why? If I want to detect sodium using AES, I add potassium chloride, I get a better signal. Okay, means that same concentration of sodium that I want to detect. If let's say I add KCl, potassium chloride, into my sample solution, sodium sample solution, I get better signal, greater signal, as compared if I do not add potassium chloride. Why? Why? This is about what? What subtopic we are talking about?
Interference.
Interference. Interference? What type of interference? Good answer. We have 4 types
Ionization.
of interference, right? Still remember we discussed we have 4 types of interference, common interference in atomic spectroscopic techniques, right? So you talking about interference, which type of interference?
Ionization.
Ionization interference, good student. So let us look at this slide. So we want to detect what? Sodium. If we add potassium, then we get better signal. If we do not get potassium, we get lower signal. Why? Because of the ionization interference. The answer is correct. So why I say that is because we know that in AES, group 1, they are low energy, right? Ionization energy low, right? This is across this periodic table, ionization energy increase. So here at the left hand side means low, means that this sodium easily get ionized to become sodium positive, Na1 positive, right? If let's say we do not add potassium, right? So now is why we want to add potassium, because potassium, the ionization energy for potassium is lower than sodium. If let's say, we do not add potassium, if we only detect sodium, we are not able to detect, because as we know that in AS, AES, and AFS, what we want to detect is a neutral atom. Either they are at the unexcited, being excited, right? Absorption and relaxed emission, right? So we want to detect neutral. If, let's say, we want to detect sodium, it's difficult because sodium easily get ionized. In order to suppress the ionization of sodium, we have to pick an element and add it into our sample solution to make that added additional things like potassium to get ionized first, right? It get ionized, then it will suppress the ionization of sodium. If you look at this, if you still remember that our pre-recorded lectures, we have this M, our sodium, right? From ground state, neutral ground state to the excited state, right? So if the energy is too high, it will continually from the excited state go to the ionized state. In order to prevent this ionized state, right, the equilibrium, we must have high concentration of electron. How to get high concentration of electron? That is, we want to add something, an element, sodium or even cesium, right, into the sample solution of sodium, so that when this potassium or cesium being added into the sample solution of sodium, it will get ionized first. Once it gets ionized, you will create in that environment high concentration of electron. And because of this high concentration of electron, it will suppress the possibility of the ionization of sodium, the excited sodium to become ionized sodium. So for this question, why we get a better signal is because with the presence of potassium, right, in the sample solution, the potassium get ionized first, right, and it create high concentration of electron to suppress the ionization of sodium. Because in AES, not only in AS, in AS, in AFS, what we want to measure is the neutral, excited or unexcited atom. Neutral, this is neutral, unexcited or excited atom in AS, AES, and AFS, not the ionized form, right? So the answer for this is when we add this potassium, we will suppress the ionization of sodium. Okay, so I think that's all already. 901, sorry, extra 1 minute. So we will meet again next week, yeah? Student, I shall see you again. So please remember to click leave so that the recorded video will be generated and I will post it onto the Spectrum later on. Thank you everyone and see you again next Thursday. Bye-bye. Bye, student.
Thank you, doctor. Bye.
Bye-bye. Take care.
Thank you, Doctor.